Alright, so in this video we're going to go over electrochem and also balancing redox reactions. So if we have a redox reaction, remember the electrons are going to be moving. You're going to break the overall equation into two half reactions. So you're going to have one where something is reduced and then the other where something is oxidized or gaining electrons. You're going to balance everything but H and O. Now if there is no H and O involved, just make sure that your atoms are balanced, that your charges are balanced on both sides, and then basically you could add the two reactions. Now, if you have hydrogen and oxygen, then you would have to follow the rest of these steps. You're going to balance the O by adding water. You're going to balance the H's by adding H pluses if it's an acidic solution. Well, actually for both acidic and basic you would do this. Then you would add electrons as you need to, because you want your charges to be equal on both sides. Then you're going to multiply each half reaction by whatever numbers to make sure that the electrons cancel at the end. And then you're going to add the two half reactions and simplify. And then of course go back, double check, make sure your charges are balanced. Now, if you have a basic solution, you would have to do this last step where you would have to cancel out the H pluses by adding hydroxides. So remember, if you have an acidic solution, you should have hydrogen ions somewhere in that reaction. If you have a basic solution, at the end you should have some hydroxide in there. Alright, so now let's just practice this. Alright, so we have a reaction here. We're going to break it into two half reactions. So I need to figure out what's being reduced and what's being oxidized. So we have a +2 and a +3 here. So in that reaction, it's being oxidized. The oxidation number goes up. So that's one reaction. So let's go ahead and finish this one. We have a +2 and a +3. Now also, the only thing I have here is one iron ion on both sides, so I don't need to worry about oxygens, hydrogens, or anything like that. So I'm going to add electrons to the more positive side so that the charges are equal on both sides. So I'm going to add an electron right here. +3 and a -1 gives me a +2, which is what I have on this side. So now I can just leave this one alone. Alright, so now let's look at the other reaction. MnNO4, and it goes to Mn with a +2. Well, right here, the oxidation number should be +7 because oxygen is -2. There's 4 of those, so that's going to be a -8. Well, I need it to be a -1 overall, so I need a +7 here. So it's going from a +7 to a +2, so in this case it's being reduced. Alright, so now I have Mn, I've got one on each side. If I had an unequal number of MNs, I would need to fix that too. But right now I've got this oxygen here, and I have no oxygen on this side, so I need to add water molecules to balance that out. So I need 4 oxygens, so I need 4 water molecules. Alright, so now I've got hydrogen on this side, so now I need to add hydrogen to this side. So I'm going to add 8 H pluses. Now my H's are balanced, my O's are balanced. Now I need to fix my charge. So I've got +8 here, -1 here, and on this side I've got a +2. Well, I need to add electrons to the more negative side, or more positive side. So I need to bring it down to a +2. Well, I've got +7 overall. So I'm going to add 5 electrons, because that would bring me down to a +2. Alright, so now I have two half reactions that are balanced. So now I'm going to combine them. Well, I've got 1 electron here and 5 here, so I'm going to multiply this by 5. So it should be 5 Fe +2. Remember, the reason we're doing this is so that at the end we can cancel out the electrons. Alright, so now I've got 5 electrons, I can combine them. So let's add up our reactants, or actually, does anything cancel? Electrons will cancel, and that's it. So I've got 8 hydrogen plus 1 MnO4 plus 5 ions right here. So I'm just combining the reactant side. Now I'm going to combine the product side. Oh, plus 3. Plus 4 waters. And of course, if this were a basic solution instead of acidic, I would go back and add hydroxides to the side to get rid of those. Oh, and then I would add hydroxides to both sides. Don't forget to do that if it's basic. All right, so now I have my balanced redox reaction. All right, so let's look at a redox titration. So a redox titration works the same way that an acid-base titration works. It's just, in this case, you're going to have a redox reaction. So you're going to have the transfer of electrons. Potassium permanganate is often used in redox titrations. It's kind of its own indicator. So if we put it into a solution and it goes clear, we haven't gotten to the point where it has fully reacted yet. All right, so in a redox titration, we have 21 milliliters of a 0.15 molar solution of potassium permanganate. It's required to oxidize 25 milliliters of Fe2+. Calculate the molarity of the iron solution. Okay, so if I want to calculate the molarity, I would need volume and the number of moles. Well, I have the volume of the solution. I need to get moles of the Fe2+. Well, I can do that because I know how many moles of potassium permanganate I reacted with it. So I'm going to use stoichiometry to do that. So 21 milliliters is actually 0.021 liters. Because we're dealing with molarity, it has to be in liters. So we're going to go to moles of permanganate. So moles, and we're really just focusing on the permanganate because that's what's really reacting here, and it's a 1-to-1 ratio in this compound anyway. All right, so now I'm in moles of the permanganate, so I need to go to moles of the thing I want, which is iron with an Fe2+. All right, moles on top of moles, check coefficients, so it's 1 to 5. 5 of these for every one of these. And at that point, I have my moles. So let's go ahead and solve for my moles of iron. I get 0.01575 moles. But that's not what it's asking for. It's asking for the molarity. Okay? So now I need to divide that by the volume of my Fe2+, which is 25 milliliters, or 0.025 liters. So if I do that, I get 0.63 moles per liter here. All right, so if we have a titration, they're asking for molarity, you can use stoichiometry, and it's pretty simple. All right, so in electrochem, we have galvanic or voltaic cells, are also called electrochemical cells. Really, essentially, it's a battery. It's where you have two half cells that are set up and they're connected and they generate electrical energy because it's a spontaneous redox reaction. So basically what you'll have is you'll have two cells. So you'll put some electrode into a solution of its own ions. So copper would be put into a solution of copper ions, and then silver in this case would be put into a solution with silver ions. Now what ends up happening here is that the electrons will be removed from the anode. So the electrode that has the anode will have oxidation happening. So oxidation is the loss of electrons, reduction is the gain of electrons. So basically you're going to pull electrons off of one of the metals. They're going to go through the wire and then they'll go to the other electrode, and then at that point the electrons are gained from the ions in the solution here. So really what's going to happen is there's going to be an exchange between atoms and ions in the solution that you have. Now the electrons will travel from the anode to the cathode, Now the salt bridge will complete the circuit. So the salt bridge is very important. It will not work without the salt bridge. And if you remember, we did a lab where you saw the voltage was 0 without the salt bridge. It connects the circuit. So, or it completes the circuit. And basically, when you have this redox reaction happening, and one of the solutions, cations, are being removed from the solution, and the other cell, you have cations that are being added to the solution. So this salt bridge will fix that, essentially. So if you have cations that are coming out into the solution, the salt bridge will provide a way to balance that by adding negative ions into it. And then positive ions will be added to the other solution. Okay, so the electrode that is more positive, E value, will be the electrode that's being reduced. And reduction is the gain of electrons, so in that electrode you're going to be gaining electrons. That'll also be the cathode. So the cathode is where reduction happens, or you can think red cat, which ends up being a positive charge. So think red cats are positive. The electrode that has the more negative E value will be the electrode that's going to be oxidized and gains the electrons. So that's going to be the anode, which think annoying ox, which is negative. So annoying oxes are negative. All right, so again, what's basically happening here is you have two electrodes that are set up. One of the electrodes, the anode, will lose electrons. So essentially what's happening is the copper atoms that are here are going to lose electrons, and when that happens, they become cations and go into the solution. So I'm pulling atoms off of this electrode and then pushing them into the solution. So the copper becomes Cu plus 2, and then the electrons will end up traveling down this wire into the other electrode. So I'm depositing ions into the solution. Well, if you weigh this before and after, you should see the weight or the mass go down. It decreases in this case because I'm removing atoms from this electrode, putting them into the solution. So I'm not going to weigh them when I go to weigh them after the reaction, or those atoms that were lost. So after the electrons travel towards the other electrode, towards the cathode, what's going to happen is that you have these electrons here and you have positive ions. Those positive ions will be attracted to those electrons, and then what you'll have is atoms that will be deposited onto this electrode. So this mass goes up, or goes down, and then this one will go up. And it's not because of the electrons. Okay, the electrons are moving, but the mass comes because these ions are getting deposited onto this metal electrode. So if I weigh it before and after, I'm weighing more atoms than I had originally. So it's not the electrons that are decreasing or increasing in mass. It's the fact that you're exchanging ions and atoms in these solutions. So when all of this is happening, so if these ions go to the electrode and attach to the electrode, I'm missing positive charges. So if I'm missing my positive charges, the salt bridge wants to replace it. And in this solution right here, I'm pulling the ions into the solution, so I'm making more positive ions. So to balance that out, the salt bridge will deposit the negative ion that's in the salt bridge. All right, so if you want to get the E cell value, so basically if you want to get the voltage generated from this reaction, you would take the E value of the reduced electrode and then subtract the oxidized electrode. Now this equation is not on the reference sheet. So if you remember it, great. But if you don't remember it, what you need to think is when they give you an E value, that is for the reduction reaction. So what you could do is the thing that's being oxidized, you're going to flip that sign and then just add them together. but do not do both, because if you do both, then you're not going to get the correct E value. And remember, because this is a spontaneous reaction, your E value should be positive, okay? Because an E value that's positive is a spontaneous reaction. So if you get a negative E value and it's supposed to be a spontaneous reaction, something's wrong. So reduced minus oxidized, or you flip the sign of the oxidized and just add them together. Don't do both. Pick one. All right, so let's look at this reaction. So we have copper, and it's becoming copper solid, so it's being reduced, and then this is being oxidized. So I was given two E values, one for copper and one for zinc. Okay, so what's being oxidized, what's being reduced? The thing that will be reduced has the more positive E value. So copper will be reduced, and then that means this will be oxidized. So instead of it adding electrons, it's going to be losing the electrons. All right, so what's the anode, what's the cathode? Well, red cats. Okay, so the reduced thing will be the cathode. The oxidized thing will be the anode. Annoying ox. And what is the voltage? Okay, so if I don't remember reduced minus oxidized, I know that this is actually going to be this reaction. Since it's being oxidized, it's losing those electrons, which means it should be the opposite of this. So I can either take this and add this to a positive 0.76, or I could do reduced minus oxidized. So it's 0.34 minus a negative 0.76, and I get 1.1 volts. So I can either do reduce minus my oxidized, or I can flip the sign of this one and just add them together. It should be the same number, but don't do both. Just pick one method. All right, write the cell diagram. The cell diagram is not a drawing. The cell diagram is just another way to write out this reaction. So if you have a redox reaction, you should lose electrons before you gain them somewhere else. So that is always what we put down first. The oxidized thing comes first because it loses the electrons. Well, what's losing electrons? That would be zinc. Zinc is a solid, becomes zinc ions. Then we have our salt bridge, two double lines. Now we're going to figure out what's gaining those electrons. Well, the copper with a positive charge will gain those electrons and become copper as a solid. Oh, and if you do this on the test, make sure you put states of matter aqueous. Okay. All right, and then in which way will the electrons flow? Well, they go from the anode to the cathode. The anode loses the electrons, and then they travel to the cathode where reduction happens. All right, so non-standard conditions. So if the temperature is changed, or if the concentrations change of your solution, so if it's no longer 1 mole per liter, then you're not at standard conditions. So these are your standard conditions. The molarity should be 1, the temperature should be 298, and the atmosphere pressure should be 1 atmosphere. So if you change the concentration, you're going to change what Q is. Unfortunately, this equation is no longer given on the AP exam. This will probably be one of those things that I say it's a good idea if you remember it. If you remember it, that's awesome. So this is the Nernst equation, and it shows how the voltage will change if you change the concentration. So if you change this from 1 mole per liter to something else, you're going to change what the voltage is. All right, so let's say that we have this reaction. Well, if I write out Q, remember Q is the concentration at any point in the reaction, I'm going to have zinc plus over so products over reactants, zinc positive ion over the copper ion. We don't include the solids. So if Q is larger than 1, the voltage will be lower. Basically, you're going to take the log of a number bigger than 1, so you get a positive number. Well, if you get a positive number here, you're subtracting it. So that means your voltage will decrease. If Q is less than 1, the voltage will be higher. And that's going to be because you're taking the log of a number that's less than 1, so you get a negative number. If you subtract a negative number, you're actually adding it. So your voltage ends up being higher than it normally is. And remember, E naught is at standard conditions, so this is looking at what happens to the voltage if you change the concentration. So if Q is equal to 1, then the voltage is just the same. So basically, even if it's not 1 mole per liter, if both of them are the same concentration, then you still get 1, which means that the log of 1 would just be 0, so it would just be equal to what the cell voltage normally is. All right, so a concentration cell works pretty much the same way, except what you have is 2 half cells of the same components. The only difference is one will have a higher concentration than the other. Well, when that happens, the electrons will flow from the lower concentration to the higher concentration, and what ends up happening, since you have more ions over here, you have more copper ions. Those electrons will be added to these copper ions, and then you're going to pull them out of the solution, and then they will adhere to the copper electrode. Now, electrolysis is pretty much the opposite of an electrochemical cell. An electrochemical cell, you have spontaneous reactions, but electrolysis is where you add electrical energy to make a non-spontaneous reaction occur. So you have to actually apply energy to this. So the anode is still where oxidation will occur. The cathode is still where reduction will occur. But the E naught will be negative. So if you actually look at the E naught, it's going to be a negative value, which means that G is going to be positive. Because remember, G, we like when G is negative. If it's negative, it's spontaneous. If G is positive, then it's non-spontaneous. So if our E value, if our voltage is a negative number, then that means that we have a non-spontaneous reaction. All right, so you might be asked to do some quantitative analysis of an electrolytic cell. So this would be an example of what you might see. What you really need to know is there's an equation that deals with charge measured in coulombs, current measured in amps, and time measured in seconds. This is on the reference sheet. And what you also need to know is that 1 mole of electrons is equal to 1 Faraday, which is also equal to 96,500 coulombs approximately. So if you know these 2 pieces of information, and this is on the reference sheet, and I believe this conversion is on the reference sheet too. If you know this, you can do any kind of quantitative questions they might ask you on the test. So in this case, it says how many grams of copper will be produced if a charge of 2 amps is run for 1 minute. Well, I want to get 2 grams of copper. Well, if I look at this reaction, I have moles of electrons in it. So if I know how many moles of electrons I'm using, I can go and figure out how many grams of copper I'm going to end up with. So if I know that 1 mole of electrons is equal to a Faraday, which is also equal to this many coulombs, it looks like I need to get coulombs, which is charge. So I'm going to figure out my charge first. So Q is equal to IT. So my Q is unknown. My charge, or my current, is going to be 2 amps multiplied by my time of 1 minute. Well, it needs to be in seconds, so 60 seconds. So my charge will be equal to 120 coulombs. sorry. So that's 120 coulombs. Well, now I have a number of coulombs. I can go to Faradays, and then moles of electrons, and then I can go to copper. So I'm starting with 120 coulombs, C for short. Well, I know that 1 Faraday is equal to 96,500 coulombs. And then I will go to moles of electrons. 1 mole of electrons is equal to 1 Faraday. All right, so now when I look at my equation right here, I have 2 moles of electrons for every 1 mole of copper that I make. And I want to get grams, so let's go one more step and go to grams. Moles of copper on the bottom. 1 mole of copper is equal to 63.5 grams. All right, so then I go through, calculate it, and I'll get 0.039 grams of copper. All right, so G in electrochem. Okay, so again, if E naught is positive, then your reaction is spontaneous, so G is negative. If you're asked to solve for delta G, you can use this equation, which is on your reference sheet. And basically, you take the number of moles of electrons, multiply it by Faraday's constant, multiply it by the voltage it normally is. So to get the number of electrons, you can get that from one of the half reactions. So sometimes they give it to you, sometimes you actually have to figure it out. But you can get that from one of your half reactions. Usually it'll be a multi-step problem where you have to come up with a reaction first, and then you can just go back and refer to that reaction to get in.